All right, I intend to prove my theory about dipole electrons, and they are these two particles that Fermilab and CERN and they all have found, but they just see them in a bunch of debris. We saw them start as light. We could see them accelerate as light. We could see them form. These are neutrinos. As you can see, a muon neutrino, electron neutrino together, when they smash, the muon goes by itself and the electron goes into showers, precisely as you see here. So we have done what they are trying to do at CERN and Fermilab. And we did this 10 years ago. This is them just today. CERN confirms ultra-rare particle transformation, hints at new physics. Well, I showed them new physics 10 years ago. And here's what they're saying. Neutrinos, which I just showed you, notoriously hard to detect as it is, and will annihilate with their anti-neutrino partner almost instantly. That's true. But we can do this. We don't need this. We don't need any of that stuff. They are correct. We did this with light. These are the neutrinos. You see that muon neutrino, electron neutrino? Here they are here. The black one is the muon, never changes size. It's like a bowling ball. The white one gets puffy like this and has virtually no weight, but it has all the energy and it goes into a shower. These are neutrinos. They're not notoriously hard to find. They're notoriously hard to get anybody to take a look at. That's where the notorious part is, and it is notoriously bad that they won't look at this. Because this is it. This is what they want to find. They want to find these electron showers because they have an extreme amount of energy. I'm going to show you this in extreme detail, and then at the very end, I'm going to go into my history of how I got into all this, and you know, when I was in the Army and I was college, and all the different phases of my life that brought me to understand this. Because I was in the first equipment that came into this country that was electronic. And I was very successful at it. So, but I work with my hands. I could do this, not just theoretical stuff. And I did it since I was in the Army. That's what my job was, to service Nike Hercules missile sites. So I will show my whole history at the end of this. But before I do, I want you to understand dipole electron flood theory. It cannot be dismissed, cannot be denied. It's 100% certain with my experiments that I show you. There's no way to deny this. And even the Fermilab, they found the same two particles. A glowy edge around a black ball. Yes. Yes. And a big glowy one. Yes. Yes. It gets bigger and smaller. Yes. This one never changes size. Yes. I agree with what they found. They just don't know what they found. And we were able to separate those from the black from the white, which is fission, and came back to here, fusion. We did everything we want to do, acceleration of light. This is top-end stuff, my friends, and it denied by the ones we trust to look into these things. Very distressing. Okay, so here is the story. They could see these particles doing whatever they were doing, but they were just in a pile of debris. Now, we did this with light and used CMOS to see these. When I presented these particles to Fermilab and to CERN and University of Geneva and everywhere, Lawrence Livermore, everybody, I sent it to everybody. And I said, we have discovered these particles. And what I got back was that you can't see particles like this. It's just impossible. We can't do it. How could you do it? Well, I tried to explain to them that we were using light, which now they're using light. Now the new stuff, they're going to do exactly what I'm doing, and they did convert to CMOS, by the way. So I said, we're using light, not big particles. They're using particles like this. We're using particles like that. I said, they're designed to use these. They're not designed to get hit by something like that. That's why you guys can't use them. And after we went back and forth a number of times, Fermilab, they just blocked me. They don't want to hear about it because it shows that they just have no idea what they're doing, basically. To be perfectly honest with you. Don Lincoln, I got to be honest, that's his name. He's the one who can't get past it, Fermilab. He told me he would never look at anything I had to show him. I'm a tinfoil hat guy. I'm an embarrassment to science. And here I'm showing his particles right there. Those two particles are the identical particles that he has here. And they react exactly the same. These two have all the energy and no mass, and these two black ones have all the mass and knock the house over and so forth in the nuclear bomb blast, as I showed all this. So I think I've made my case. Without doubt, it's a case that's been made. Now, I'm going to show you how I did this stuff, actually did it with my hands and worked with the equipment and so forth. These people come up with all this convoluted stories about crazy ideas. And I show, everything I show material evidence to support it. And I can go back to some of the earliest days that they were experimenting with electricity in fields and how foil moved away from each other and so forth when you energized it and things like that. They don't do any of that stuff anymore. It's all, I take 27 parsecs of this and, plus they think if the light doesn't slow down, the light doesn't accelerate. You can see it's accelerating. I can show it slowing down. We've done all of that stuff. Here it is slowing down, coming in fast, slowing down. To block me with all this evidence as a public, we're paying the bills at Fermilab, but I should be able to show this. And, even say with NASA, same thing too. They're talking about Webb, Hubble, we can see, now we know a bazillion, trillion, zillion miles away. No, light slows down coming through this, and it slows down, I would say, fairly quickly. The universe is just saturated with particles. They think it doesn't slow down. Obviously it slows down. And this is the other thing. This is the killer. As I showed you, these are electron showers. You see those? Those are electron showers. Nobody can say that's not true, because this is from CERN and Fermilab. The muon neutrino, the electron neutrino together, the black and white, the muon goes sterile, the electron goes into a shower. Here it is. This is what it is. So these are electron showers. Now, what do they have to say about electron showers if you can create them? Well, here's what they have to say. CERN specifically. All right, listen to this now. Listen carefully. They are trying to start with protons. So they're going like this. Bam! Creating all kinds of debris. A large number of hadrons are produced. Just garbage. Now, the hadrons are bits and pieces. So here's what they did. They took two of these and they hit them head on, and now they got hadrons. Well, what is a hadron? It's a chunk like that, or it's a chunk like this, or it's bits and pieces. So the hadrons decay. Now, when they decay, they create a large flux of high-energy neutrinos. I showed you the neutrinos, the black and white balls. The black one is the muon, and the white one is the electron neutrino. And they're created neutrinos and antineutrinos, that's what they call them. The Diracs, they think they're positive. They're positive and negative. Call them neutrino, antineutrino, that's fine. All flavors, because they have all the different flavors. I show you that in my stuff. Now, that gives them a data set of electrons and muons. We started with that. All of that you don't even have to think about. We started with electrons and muons going through a tiny little venturi. And what happened? The energy, now listen to this, they had finally got down to electrons and muons, the energy of neutrinos interacting within this experiment. Phasor V just means their experiment. The energy of neutrinos within this experiment was a few hundred billion gigavolts. A few hundred billion electron volts, all the way up to a few trillion electron volts. What you're starting with here is in the mega electron volts. It's just staggering, the increase in energy of the neutrinos. When you can get the neutrinos apart, they're just absolutely stunningly hard to pull apart, and that's why they come back together so strong as electricity. And that's just pushing that white stuff all by itself. And we let the black slap it through. We didn't have to do a damn thing to it. It just happened automatically because of the Venturi. Just think of this now. If you could carry this thing around with you and have any kind of outlet you want, any voltage you want, USB, AC, DC, 50 cycles, 60 cycles, it wouldn't matter. All housed in here, just using with a bunch of, thousands probably of these little lasers, and their Venturis, and then a harvesting, which now they have some new materials, perovskites, and they have all different transition metal films that they can absorb most of this energy and conduct it down as photons. And this is a photodiode. Now, there won't really be photons. There'll actually be just the white part. There'll be neutrinos. The only thing that'll be coming down here is electron neutrino. The black part doesn't come here. Photons have both the black and the other part. All right, don't forget now. This is critically understand this. The black and these together are photon. That's not electricity. That's light. It bounces. This is electricity. This is where the white is ripped from the black, but you got to get it before it comes back to the black again. So this is fission, this is fusion, and in between you got to grab that white, send it down through a battery, and then you use it to do anything you want with it. And there it is right there. But you have to understand electron flood theory. You don't understand electron flood theory, you don't understand about breaking the black and white particles apart. Now, what else is beautiful here? We can adjust the pulsation of the laser and just increase it. Maybe you just hit it really, really fast. You're going to squirt a whole bunch. Maybe you just slap them slow. I don't know. You can have all kind of different colored lasers, intensity of the lasers, the wattages and all that stuff. All of that is up in the air right now. That's got to be engineered. I'm not going to do this anymore. Everything I did, it just got me blocked more and more. And that's academia, and that's our government agencies. That's our government agencies doing this to us. They don't want to solve this. They don't want solutions. Solutions that takes funding. And that's why I'm not kidding you. It's a terrible, terrible situation. But that's all I can tell you. I can see. And again, these are the Higgs fields. It's exactly what they've been looking for. We can squirt these out in just gobs. Gobs. Look at that. That's that white spray coming through there. The black can't get through. Although a few of them here and there coming through. Not many. And the black is just laying out here waiting to hit. When the white hits it, they go off into these little fields, the Higgs fields. So once again, if this doesn't get looked at, it's a shame. It's a true shame. It's an absolute true shame. Low energy showers, building to high energy showers. This is where we harvest right here. Prior to them reattaching, because they're going to jump back to muons. Not the same ones they left. So entanglement is kind of silly. In other words, when that thing goes through here, the light, here it's the black and white particle, black and white, black and white, black and white, and then it explodes. The black stays here, the white goes there. The blacks don't jump over from here to there. Not in my mind. Unless you can think that's true. I don't. I say these ones here left and just mixed in with the rest of the stuff here. And these were waiting around because they were dissolved. In other words, I think there's extra black particles laying around. That's the only way I can see it. Because if everything was attached together, where did these come from? Where did those black ones come from? I know where these came from because they got knocked off of these white ones. But where did these come from? If these didn't jump over to here, which I can't believe in my wildest dreams they did, but again, I don't know. Maybe they're just so powerful somehow. You'd see them. You would see them. And the reason you would see them, you never ever have seen dark matter. Nobody's ever seen it. We're the only ones that ever seen it because it's on top of the white. Let me show you a closer shot. Okay, I'm going to go into, like I said, I'm going to go into a rant about how I got started with this and how it's been suppressed since the day I realized everything was a dipole. We would be so far ahead now if they'd even just looked at it. It was refused, and still crushed. This, as I showed you, is light accelerating. Now, if you cannot understand that, I don't know what's wrong with your mind. This is not, well, it's just beginning to accelerate. That's why it's glowing. But this is full-fledged rocket ship acceleration. That's acceleration. All right. This is what we're going to be looking at right now. The black and the white particles were attached. They detach. They reattach here. And the black one is the same size particle everywhere. And why do we see it? Nobody else in the whole world's ever seen it? Because it's sitting on top of the white. You see it? That's the only reason we can see it. It's sitting on top of the white. Black doesn't emit anything. It doesn't absorb anything. And it doesn't reflect anything. The only thing it can do is obstruct light. And that's what it's doing here. And it's doing it over here too. And it's getting fainter and fainter as you go off. There's still some here, you can see. They're obstructing some of that light. You see it? They're all the same size as the black ones. And the black ones do not care about being right on top of each other. That's why in the dipole electron flood theory, they are in the center of all the white particles. The white particles surround all the black particles. That's when the atomic bomb goes off. They push everything inside with the blast first, and it crushes all the fields into every other field, and they all bounce out. And that's why all the white ones go out first, and then the black follows. And we had the same thing happen. One of Rod's experiments shows that too. You see that coming right through the Venturi here? It let some of the black come through with it, and the black just pushed the white. And then that's the Whistler waves in front. I think I showed this during the atomic bomb blast. I know this very, very well. And I will speak to anybody, any physicist anywhere. And they won't speak to me. And like I said, I went to the University of Geneva online. And I told them all about this stuff. And by the time I was done, I don't think they were arguing anymore. And again, they did shut down CERN. Hold on. Did CERN upgrade to CMOS detectors? And this was after I talked to him. I don't know if I had any effect, but yes, CERN has been exploring and implementing CMOS technology in some of its experiments and detectors. Yes, because they're coming down to my size stuff, light. They offer advantages, everything. One notable project in the development of CMOS sensors, a Large Hadron Collider, particularly for the upgrades to the Atlas and CMS detectors. Now, they're just doing what we did. And this is the Phaser LHC, visible particles, particle physics experiment located at CERN's Large Hadron Collider. But it's in the little bits and pieces. They didn't need all that stuff. You don't need all that stuff smashing things head on like this. All they're doing is pushing the fields together, and normally the fields will bounce off like that. So they only get a couple of hits out of billions of particles. We're funneling all of our fields, all of them in front of each other. They can't stop. There's no way they can get out of the way. And if because the design is like this, coming straight down in, and then it's got all those fields have to crush down, and they're crushing against each other. That's why field to field makes a glow. There it is. I don't know how much more I can show of this without anybody paying any attention. And that's what's happened. Not only not paying attention, being actively suppressed by CERN, by everybody, but Don Lincoln specifically at Fermilab. Now, I don't know anybody else at Fermilab pays any attention to anything, because I slaughtered everybody I could think of. And all over the government agencies. I mean, we need to get free energy. If we could get free energy from that, I can't imagine anything that could be slicker than that, carrying around a little lunchbox and being able to use it for anything you want. drive cars and all that. And because this white stuff has no mass whatsoever. Your car weighs 4,000 pounds and it's all electric. You fill it with electricity, still weighs 4,000 pounds. You drive 500 miles, you don't have any more electricity, 4,000 pounds. You come back, you fill it up with electricity, 4,000 pounds. Never changes. Gasoline, you take 10 gallons, it's 60 pounds of gasoline. You're combusting. This, you're doing nothing. You're just splitting. You're splitting. And it's conservation of energy and matter, yes. There's no question whatsoever. But when you split the energy and it has to come back together, you get the same amount of energy when you bring it back together. So that's the key. A huge amount of energy is generated, but by itself, because of the pulsation of the laser and the design of the Venturi, squirting that energy out. Okay, I'm going to be talking all about myself, my experiences starting from when I was in the Army, and then I went to college, and then I went into business. And one of the things that I was hired for is to introduce electronics to the business world, because at that time there were electromechanical machines and business machines. They'd go boom, boom. I'm serious, it was crazy. But I knew about the electronics, and he hired me. This guy who was a regional guy hired me as a field engineering manager to bring this equipment in. And I'm going to talk about what happened. It literally exploded, and it was because of the chip. And I figured this out. I think I'm going to talk about this later, but the machines literally exploded on the desks, and they did because they were too cold. And the fibers inside of these microprocessors are so tiny that if you have more electricity than you're supposed to, they'll just explode. And they literally did. Every single one of them did. And I'll explain the circumstances. And it was because they tried to use a 17-volt logic chip. This was General Instruments. And they worked fine. At 70 degrees, they were fine. And this was in the 1970s when I was with Victor. I was a field engineering manager. It was a 17-volt series. The chips faced significant, yes it did, reliabilities, particularly regarding their performance under specific conditions, cold primarily, because the increase in amperage as you go colder and colder is absolutely staggering. I was shocked because I did all the research on this. I was the first one to install these, and when they went in cold, they exploded. Now, and then I asked again, did General Instruments make a 17 volt and it failed, and they now use 5 volts? He says yes. They produced a 17 volt chip in the 70s, faced reliability issues, led to its limited adoption. They only could use them if it was over 50 degrees or something. You couldn't use them when they were real cold. But anyway, so they took them out of service and they changed everything. And they went down to 5 volts. And so over time, the industry shifted towards 5 volt standard, because 5 volts, you're not going to explode those wires. 17 volts, when you get cold, the increase in amperage is staggering, and then it just exploded. So anyway, that's I'm going to be talking about myself. I'm going to tell you how I all ran through this, because this is how I got into this. I had to understand all of this stuff, and I had to face all of these people that well, my professors and all that stuff. I finally just had to walk away from that. You can't get anywhere. I still can't get anywhere. Velikovsky never got anywhere. He wouldn't even be known today if I didn't put my book out about him. Nobody ever pays any attention to, they are now a little bit, but that was 10 years ago. So the things do not change, and that's why I get frustrated, I get upset, and sometimes I lash out a smidge. Anyway, this is going to be about my history, my friends. Okay, my friends, today I'm going to explain dipole electron flood theory, and then I'm going to go into a big long thing all about me and how I arrived at this, because this was started in 1968. These papers here go back to 1970, where I did my dipole electron flood theory, I knew everything was a dipole, is that there's two types of intermolecular forces, dipole to dipole interactions. There's polar and nonpolar. And you have to take into account a whole bunch of little things, but the end up result is the transfer of energy is from light to atomic vapor. Light is atomic vapor. And when I say atomic, I mean dipoles. And I come down here and I talk about how electrons, the differences in the nucleus, and therefore Rutherford's atom was wrong. And I go very, very, very deep into this, and into every range, chemistry, of the electro, thermo, everything, every single thing. You have to understand it all. You don't understand anything, and that's what I did. Okay, my friends, I believe I have talked to you about my dipole electron flood theory, which is right here. We'll see in a moment. But these are the dipoles. There's a black and a colored one. I've shown this many, many, many times. And here is my theory that these are the two particles. But the black congests into the center, congeals in there, surrounded by the white. So they've never seen the black. And the black is in everything you're looking at here. Everything there is, inside of every atom, the core is black. They come together, but they're only made of these two particles. These are the particles that make the nucleus. That's it, done. There's a dark muon, never changes size. Exactly what Fermilab says. I agree with that 100%. Then there's the electron. Now, I show it as white here, but it comes in all different colors, and white is the most brilliant, which is basically all the colors put together. Now, this is going to be the difference from the standard model. A standard model has a big, huge proton like this, and a couple of little electrons around it, depending upon how many protons they say. But the proton is gigantic. The electron is, they don't even really count the weight of the electron. It's so small. But they're supposed to have the same charge. It's just not correct. There's two pieces just like this. And they know that right now. They call them gluons. But they're actually the electrons. So these two together, which we separated, that's the key. Sometimes they come in different color ranges as the neutrinos build up to the full photon range. Now, the gluons are nothing more than electrons. That's an electron. Nobody ever suspected it. Nobody knew about the black part. They knew there was a glowy part. The electron is static discharge, lightning, electricity. They knew there was an electric negative, but they didn't know about that. But they did know there was one of these laying around somewhere, because now they call them gluons. Now, two gluons back to back make a photon, and that's what I showed you in our experiments. It changes some things, not a whole lot. It's chemistry a little bit, space a lot, redshift just goes away. That's just nonsense. Light slows down as it comes through all the medium in space. The medium in space is dense, my friends, absolutely dense. This is what's out in space. You ever see this space telescope? You see all this stuff everywhere, but light never slows down. I'm going to tell you right now, it's an absolutely zero question that when light bangs into these fields, it resists it. And as that happens, the light gets stretched longer and longer into the redshift. It loses energy. It was up here coming, and it starts banging into things. It's and it gets down real slower and slower and slower. That's all it is. Into the red spectrum, and then it goes into the microwave background, which is just not even moving. It's just sort of laying out there in space, and then it gets banged into, and light blinks on and off, as Don Lincoln says from Fermilab, right here. This is Don's statement. Same time frame, 2013. Empty space isn't empty. Agreed. Well, what does it do? Empty space experiences subatomic particles winking in and out of existence. Subatomic particles winking in and out of existence. Subatomic, smaller than atoms, flicking on and off. They're getting hit by another pieces of light. These particles are real and have a measurable impact on our universe. I agree. Why don't they take them into account for the redshift? They say that everything's going so fast now, pulling away from the Earth, that they're just pulling the light, so the light is going this way, so we end up seeing it shift way down to here. No, 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 no. It comes like this and goes bang, 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 bang. And it gets slower and slower coming to us. It's unbelievable they can't pick up on that concept. You think so, everything's going to go through there at the same speed? And if you see the pictures of the galaxies and the things coming back from Hubble and Webb, they just show you it's littered, just 100% littered. Even my little diagram here, my little picture, it's just like this. It's everywhere, everywhere, and everywhere is like that. And every one of these light particles, I show them here, is going real fast spinners and slow spinners, and that's a reflective spinner. They all have energies. Some of them are real high energy, some of them are not so high energy. But they're coming from the sun towards us. There's just no question about it. And they're particles. So space is 100% saturated with particles. Here's the light particles. Light is light. That's light. It's a particle. And it makes a wave because as it comes through the air, the wave is like this. The particle's way back here. The wave is way out here because it has a field around it. Particle inside the field. Everything glows out here. Once it passes, it stops glowing. You see it? Once it passes, the wave passes by. These guys got to get out of the way. These guys just chill back out. That's the wave going through. I want somebody to start challenging me on this. Can't they see acceleration? Can't you see that that light is accelerating from this phase right here? It's starting to accelerate. Otherwise, you wouldn't even see it. It's starting to accelerate and pushing the other stuff out of the way. If it doesn't push the other stuff out of the way, you won't see it. But here, it's really pushing. And it's starting to rocket ship. And the only reason is because there's a Venturi here. And a Venturi is known as an accelerator. It's as simple as that. Light is almost identical to water. And it's just, and it takes off. And right here, it explodes. And the reason it explodes is because of the strong nuclear force is being ripped apart with literally tons of energy. Literally tons it takes to rip the white from the black. And that's what we did right there. You see it? The black and the white are stuck together. And this is it. That's the normal configuration. You're not going to rip those apart easily. In the atomic bomb blast and so forth, yes, they'll come apart. But not in the normal life. And here it is right here, into the Venturi. And we're accelerating light. It's acceleration of light. Einstein was not correct. Just get off that case. And here, it literally explodes. And he shows these other light fields are all over the place in here. But you can't see them because they're not in a concussive mode. This is going this way and it's coming back because it's stacking up to the Venturi. It can't get through. And it slaps. The black slaps the white. You see it slapping it here? It's going poof, poof, poof. The white is shooting through here. Only the white. And the reason is the Venturi is so tiny that only the white can get through. You have to tune the Venturi. You know, this is Rod Warren stuff. I'm not taking credit for any of that stuff. He did this just absolutely stunning, the work he did. And never paid off in 10 years. More than 10 years. So eventually what do? You go about your life if you're smart, but I didn't do that. Anyway, here it is. These are the particles. This is the light accelerating. Pow! There's the particles. Those are photons, and that's a downspin because the white particle's down. That's an upspin because the white particle is up, going this way. And they're all oriented towards the Earth. And the green is the same. And you see when I say it's oriented towards the Earth, you see it straight up and down this way, even though it's going that way. It's not spinning this way. It's spinning straight up like this, even though it's going off to this direction. Why would it do that? It's because it's polarized towards the Earth, and these are the neutrino phases. So the photons are very well understood now, and CMOS can see photons. This is the thing. They gave me so much trouble because you're an idiot. Who do you think you are? I mean, really, it was not pleasant. And I said, no, CMOS is a different thing than you're doing. You're using, here's what they did. They took this. You got protons and neutrons. bam, and they get all this garbage. Now, when they show an X particle, that could be this, it could be that, it could be this, it could be that, it could be this. They're just chunks of debris. We started down where the light is. Now, they see some photons kind of bright, and they see some photons almost not bright at all. You see this? That's a little photon, same thing as we have, and they see them bigger, like, you know, brighter, and they see them not so bright. And then they see the particles that fall off. Even look at this little bugger. Same thing. They keep seeing all the same particles that we have. And then they see these pieces that have broken off of these. Yes, exactly. Identical. No difference. What we did. Send the red light through. It smashed here. The white particles squirted through. The black particles came away. We got the Higgs fields. We got the photons. This is the one that is real. That's not normal. And I know why this happened, because this was a reverse spinning field coming down here. You see it? All by itself, like spinning backwards when it should have been spinning the other direction. And it was spinning this way when it should have been spinning this way. And when it interfered with this one down here, this one's spinning the correct way, ripped that particle off. Now, is that the same size? And I think it is, because it just diminishes here, it just stops. It's like ripped away, so there's no more field. That's my take. I've studied these very deeply. All right, so I have every right to speak in this realm. I've done it my whole life. Now, don't forget, these are what they're talking about to be the smallest particles that exist, the Dirac neutrinos. And we separated those, the black from the white, as I showed you, right here. Black from the white separated. And the only reason, because it couldn't get through the Venturi. And we didn't do anything, we didn't add any extra energy whatsoever to make this effect happen, which is to tear the white away from the black. It literally is squirting that white through there. And if we can harvest that on some kind of a collector right there, I don't see why we shouldn't be able to get something out of that. I would say be free electricity. And you can see that the black pushes the white. You see the black? Pushing the white ahead. You see how tight these fields are? That's because that's right at the explosion. This is what's called a Whistler wave. This is just magnetic. This has everything with it, as the heavy-duty particles along with the white particles. But the white ones precede the black ones. They always will in this kind of extreme explosion. And that's what this is. That's a subatomic nuclear explosion. That's what it is. And it sends off Whistler waves. Same as an atomic explosion. Atomic explosion does the exact same thing. The bomb goes off. Boom! And you're way away, and all you see is smoke come up, and you see a flash come by you, and you will actually hear, which is the Whistler waves. And then as the black and the white separate out, a house burns down here, just completely burns, smokes up, doesn't even move, because this has no weight. And then the black hits it, and off it goes. Shown that dozens of times. You can look it up. Teapot atomic bomb blast experiments. And you can see it. Very simple. All right, this is from a video I did a year ago. So I'm pointing these things out on the screen. I'll explain to you what you're seeing as I go along. The bomb just went off, and the house is just smoking up. It's not going anywhere at all. Nothing. Boom. Now comes the black part, and it just smashes and goes away. All right, so I'm pointing all these things out. Now, what does that tell us? That there were two separate particles. Let's come back to the beginning here. Right here, watch. It'll go off, and you just see brightness, and then just smoke. No weight whatsoever to the first particles. Watch. Boom. Here comes it. Get ready. Boom. Now, I just stopped it. All you're seeing is brilliance. That's the white, and there's no weight to it. It has no weight. But it's got all that energy to burn. I cannot totally explain that, how that energy is created, but it is. and it has no mass. And this is also, the Don Lincoln at the Fermilab said, exactly, that's correct, no mass. And then the black has all the mass. Watch. It's just smoke. I'm going to stop it again. Just smoking, smoking. Look at the poles in the background. They're all smoking up. And anything that can absorb electrons. The metal can't, and the side of the building can't because it's coming this direction. Now watch. Just smoke, 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 and now all of a sudden, boom. I just stopped it again. That's when the black particles hit. That's pretty conclusive that there's two separate particles there that are emitted from an atomic bomb. There's no question. Okay, listen to this. I showed you the white particles hitting and then the black particles hitting. Well, in this case, we're going to see the Whistler wave. We're going to hear it, actually, because it's an audible wave that precedes everything. Now listen. This. Did you hear that? You heard that? Brrr. That's the Whistler wave that comes ahead of it. Now it's going to be coming out here, and then way down here somewhere, it actually hits the people. All right, because it's coming across the desert now, and it takes a while. Go past. All right, I'm just going to cut to the chase. All right, that's a Whistler wave, Whistler radio wave, very low frequency electromagnetic radiation. They say it's caused by lightning. Well, this is basically the same thing, an explosion of the white particles. So don't forget, this is that Whistler wave right here. That's the ultra low frequency. You can hear it. And I asked Rod if he ever heard anything, and he said he thought he could hear a crackling every now and then. And I'm sure that's what he heard this here. And this is the white that pushed all those magnetic pulses. There's nothing but magnetism there. That it doesn't involve any black particles at this point. The black particles are pushing the white particles. But this created a vibrato in front of it, and then it starts to sweep its way across the black. All right, let me explain to you why this is misunderstood. They are slamming gigantic particles together like this, and they get all this debris, or just nothing but debris, and then they dig through it. Well, they have found these tiniest particles, which I showed you before. They found these little bits and pieces that come out from this particle zoo, they call it. And it's a zoo of particles. But they see the same things over and over and over and over because this is semi-stable. Well, it's stable. It's a photon. That's a little tiny stable photon. These are not stable. These are not stable. Not stable. They want to find partners. But this is the stuff that comes off. But they see all of these all the time, and these are the tiniest particles. We see them, but we see them come from their own source, which is light. That is just standard laser light. No big fancy. It's a construction laser. It pulses. Boom, boom, boom. And it does all the work right there of dividing the particles. We didn't add anything extra. This could be in a lunchbox carried around. And if you could harvest that electricity right there, I don't see why you couldn't have portable, cheap, safe, basically free electricity. This stuff is off the shelf. Lasers, they're right there. Photodiodes, they're right there. Converters and so forth to make the, well, let me just show you my concept. Just to get this out of the way, can CMOS see photons? Yes. CMOS, which is complementary metal oxide semiconductors or silicates, however you want to use it. These CMOS sensors can detect photons. Yes. And that's how they function in applications like digital cameras and imaging devices. That's what they're there for. They get turned on. There's little, almost like transistors, when they hit the base of it, it turns it on and it sends it a little shock wave into the processor. And it says, I just got hit with a certain frequency and a certain intensity, which relates to whatever color it is. And there's a whole array of these sensors, and they pick them all up over the place, and then they amplify them. This is not, it's not hard to do. And this was being done in 2012 with their Samsung Galaxy S3. That's what took all these pictures. That's what took that picture right there. And that was the, well, here's the camera. Here's the camera. Galaxy S3. 2012 that came out. And Rod Warren is the one who was taking these pictures, and all he did was use this, a pulse grid laser. And he hit the laser through the Venturi, and only the white could get through, and all the other ones, the black particles, stayed this way. And when I saw what he did, I freaked out. Now, here's I'd like to see somebody try this, to see if they can get an over voltage. I'm done trying. Everything I did, nobody paid any attention, so I could do this all day long, and it's still not going to get any attention. Somebody else has to do it and present it to somebody that will listen. Somebody from a university that has a student that says, wait a minute, you guys are wrong. But that kid will probably get failed. That's the problem. It's really depressing, the state of education. Absolutely disgraceful. But the laser shoots out here, black and the glowy part. The black stays back, the glowy part, that's all you want to go down in your battery. And this, you put a photodiode in there, it means it gets through here, there's a gate, it goes through the gate, it can't come back out. And that's it. You store it in your battery, there's a couple little regulator devices in here, nothing sophisticated, and then you run it through whatever devices you want. You tap off a little bit of it back to the laser to make the laser continue. And the way I understand it, the electron showers here are extremely high energy, and they come in at low energy and they go to high energy. And that also, CERN says that's true. All right, this is CERN. It's exactly what I'm showing. Coming through the Venturi, they come in at low energy. You see here, low energy showers? And then high energy showers they turn into because they keep hitting other electrons. This is the electron showers. All right, this is low showers, energy, high energy. Swish. These are the muons, which is a black ball. They can't get through. They bounce back out. Muons have the shower earlier. Well, they didn't shower. They just wouldn't go through. And this showers later and coming out of the Venturi, which is what we did. It's right here. This is not a mystery anymore. The mystery is why they won't do their job and look into this. This is not. I've been very, 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 very vocal about this. And sometimes I get a little frustrated and I get kind of nasty. But, you know, we're paying billions and billions and billions. I don't know how many billions to Fermilab to do nothing. They won't even look into this. I submitted this to them. I said, we found your particles. Go away, you're a tinfoil hat guy. 10 years ago. Never turned around yet. Never, and just within the last few months, same thing. Don't ever contact us again. You're an embarrassment. All kinds of stuff. And these are the people who were paying billions of dollars to find these products. We found them 10 years ago. And we could have probably helped the planet, helped humanity. It's not allowed. Blocked and ignored. And we found everything they found and much, much, much better. And it upends everything they say. That's the problem. Here's your Higgs fields. Those are Higgs fields coming at us. And they can change a little bit of colors when they get impacted hard. You see? Here's some more. That's really serious, serious white. And that's the division of those particles. That's right here. That's fission and fusion. Fission right here, the black came away from the white. Fusion when the black came to the white. In the middle, you got raw electron showers, just like I showed you from CERN. They agree. There's no disagreement here. Low energy showers, high energy showers. The muons back out. It's exactly what I showed you. Now, I don't see why we can't use that, because when you look up, well, hold on a second. Okay, my friends, this is going to be all about me. It's just the way it's got to be. I found these same particles that Fermilab found. This is 2013. We found them right about the same time. And I actually contacted the people at Fermilab, and they dismissed it because they said CMOS couldn't see these things, and we had a big long discussion about it, and it proves that yes, CMOS can, and CERN actually, I went to the University of Geneva, and I explained it to them too. And CERN, right after that, I don't know if I had anything to do with it, but they shut down for 3 years to install the CMOS detectors so they could see without interfering. CMOS stands back and it absorbs, and it doesn't have any interaction whatsoever. The observer effects always said, if you look at it, you change it. No, it's not because you look at it. It's because you push energy into it in the form of light or something you're putting into it, or you're putting something into that field that absorbs some of the energy. So yes, when you turn that on, it says, ooh, whatever, it changes. That's the observer effect. They used to think you just look at it and it changes. I'm not kidding you. Even Don Lincoln, and this one here, he says the same thing. Listen to this. A point-like particle will not change in size, but the more closely you look at it, the stronger the field surrounding it becomes. Anytime you push something into a field, it pushes back harder. Yes. It's not because you're looking at it, it's because you're flooding it with light, with some kind of radiation. All right, I'm telling you, I know this better. And again, this is going to be all about me, and I'm going to brag my behind off because it's all true. Just a fact. You're going to see, and I'm going to show you. I did this stuff. I'm not talking out of my ears. I'm talking out of actually my fingertips. Actually, I had things I could burn my own chips. We developed our own systems, scales and scanners and all that stuff. Before anybody had any of this stuff, we had it. That's my wife and me. This goes back a long time. We had I had a great business going here, very good business, and I had a wonderful programmer who never got his due, which was Scott Cook. He did all the programming for this. I told him what we needed. We needed a touch screen, and we had scales and kitchen printers and remote displays and every kind of thing you could think of, drive-through. We had it all. And my system was so good that Sharp bought it and put it in their world headquarters on their equipment. And I had my system. I designed a lot of it around Dunkin' Donuts because we were sold them to Dunkin' Donuts, a lot of them to Dunkin' Donuts. And, they did the drive-through, and it went to the kitchen printers and everything. And all of the texts, whatever was rung up on here, would automatically overlay the cameras. And you could search by date and time and product description, anything you want. So it was a control. And it did everything, all of these things. This is kind of scruffy, but I called it Home of the Retail Appliance. So simple, you plug it in and start making sales. So powerful, it's called version 4. No feature left behind. And it was, no feature was left behind. You do anything you want. All you had to do is you put this on the counter, and the guy would say, how can I put my inventory in there to start subtracting from my inventory? I say, you take the scanner, a little handheld scanner, you go around and scan, and you say there's 27, scan it 20, and you can put the price in and the number of them right at the same time. So everything was in there. All the database of anything that was for sale was in there, basically. You may have to add some here and there, some oddball stuff, but it was a powerhouse. And I sold a lot of them. And nobody ever returned them. Free 30 days. Free trial. All features, 30 days. No info to put in the registry. You don't have to do anything. You just start scanning with it. And what they did was they put it on the counter, and the first stuff that would come, they'd scan it. And it would come up and say, enter price. And you put in $4.99, enter department, grocery. Done. From then on, there's $4.99, grocery, whatever it was. So it was a powerhouse. Now, in addition to that, I was doing all the maintenance and all the electronics, and I could do it. I knew everything there was to know about the electronics. because that's where I came from, was the electronic background, touching. And like I'm sure I'll make this point a whole batch of times, how many different obstacles we encountered. Not just me, everybody in this field. There was the issue of static, which is pretty well resolved, and which would just, the circuits would go, ah, and then you'd get a retry, re-enter, I'm lost, that type of thing would come up. And static still, you can build up tens of thousands of volts. Voltage is different than amperage. Amperage means like the quantity. Voltage means the pressure. So like you take a little squirt gun, you can squirt it 100 feet, let's say. But you take it, so you only got a drop of water this big. So you don't have a whole lot of stuff, but you got a lot of pressure. Pressure is the voltage. The amount, quantity is the amperage. And there's a whole set of circumstances that determine how much voltage you have in relation to how much amperage you have. How is that voltage established? There's so much, well, there's really not all that much to it, but for the average mind, you're going to see this and say, ooh, this is scary. It's not scary. It's not hard to understand once you understand dipole electron flood theory. And this is Don Lincoln's stuff. We had the same stuff. I found the same stuff. Here it is right here. This is what we did with our light experiments. This was not just showing little pictures. They could see these. I know they could see them, this is the muon, that's the electron neutrino. And together they make a dirac. That's a dirac, and that's a dirac. And what is a dirac? Well, that is a dirac neutrino. All right, these are neutrinos. Matter and antimatter, they call them. It's actually just the opposite. The black part is a solid ball that never changes size, and it's solid. This is the glowy part, and it's the burny part, which I would call it antimatter. It burns matter. This is a burner, and that's a smasher. And those are neutrinos. And neutrinos are the smallest particles that exist, and we found them, and we can separate the black from the white. You see this? We found those two. These are the Fermilab. This is right from Fermilab. That's not. This is just posted into my pictures. This is what we found right here. Exact same thing. The glowy edge around the black, and then the white ones or the colored ones, because they come in green, red, blue, are the colors of the laser. Now, we could see them right here. And they come attached. That's a strong nuclear force. That is tight, tight, tight. You can't break those apart. When they're together and they smash into something, they come back as light. But the light is still a ball of these particles. And it's like a little ball, and it bangs into your eyeballs. All right, now, what could we do with that? Well, we could accelerate that. And this happened just by accident. With Rod Warren, fabulous guy. He's no longer involved in it. I'm not sure why, but this is what he did. He created extreme acceleration of the particle, which was I showed you up there. And then it hit the Venturi right here and exploded, and the black separated from the white. That is subatomic nuclear explosion. That's a subatomic nuclear fission. You can have fission in a number of ways. If you break the black from the white, that's fission. If you took the whole big gigantic particle, like protons, and you smashed them like that, yeah, that's fission too. But this is fission on a much more refined way, so that we can actually squirt that white, which is what we want, is that white, which has no weight whatsoever and has all the energy, and we can squirt it into a receiver right there, I believe, and get free energy. We can't talk about free energy. I'll talk about anything I want. If we got to do something. This is a disaster what we got going, and for Fermilab to have denied me to even speak to me for 10 years is that's a disaster right in itself. And this is what I found since coming out of the Army. The Army wasn't too bad. They wanted things done. and then I was very successful in the Army. And as a matter of fact, I remember I said they tried to destroy me in the Army too. Every time you do something that somebody else feels threatened or feels like belittled by it, I don't try to belittle anybody. At this point, I'm pissed off, and I'm frustrated. But here's what happened in the Army. Like I say, I got promoted. I don't know if I told you this yet, but I'm sure I will at some point. I got promoted immediately. I had a 139 GT score, which means general technical, which means you can do stuff, not just some address in the world or something. This is technical, and that's what I excelled in. I had a 139, and a 136 is considered in the 98th percentile by Mensa. When I had the GT test, I was 139 back in 1968. So they promoted me right away. I made an E5, and when I went to Alaska, the shop that they put me in was a top secret type of thing, where you're in this confined area, and then they send you out on missions to different sites to work on the equipment out there. Primarily, it was the electronics that I did, and radar and all that stuff. So anyway, I get into this area, which is completely blocked off places, no windows, no nothing, and it was sectioned off into these little cells. Pretty good size, but blocks. They come out the side, and you go in that area, and it's sort of cordoned off. So I get in there, and they say, "Hey, Spur, we got a new guy. Da da da." Well, hey, how's it going? Hey. He said, "Yeah, Spur here. Listen." I was an E5. Now, everybody around me was an E2, E3, E4. I was like the top guy, except for the top ranked sergeant, who was E7. He just made E7. I think he was in for like 18 years. He just made E7, and that I had made E5 in 7 months, and that did not sit well with him. So he says, they're all sitting around having coffee, and waiting for an assignment. I don't know. So I go over and I grab a cup of coffee. He said, whoa, Spur, what are you doing? I said, I was going to grab a cup of coffee, sit around, talk. He said, no, here, sweep the floor. Look at the floor, it's a mess. Sweep it. I said, okay, no problem. I'm the new guy. So I sweep the floor over. I get it all done. It only took 5 minutes. I get it all done, and the sergeant says to me, he says, so then I go back to get my cup of coffee. He said, what are you doing? I said, I was going to have a cup of coffee. He says, no, I told you to sweep the floor. I said, I did. And he said, you don't understand. You swept it from there over to here. Now you got to sweep it back from there over to there. I said, what are you talking about? He says, I just told you to sweep the floor from over there back to here. Now get it done. I said, are you trying to harass me? He says, yes, and I will harass you till the day you leave. And I said, Vayos con Dios, amigo, and I walked out. And I went over to the warrant officer, who was a nice guy, really nice guy. I walked in, I said, this guy's harassing me. And I told him the story. He says, what do you want to do? I said, I want to go back there. He said, all right, we'll put you in the motor pool. So I said, good. Well, they didn't like it either. They were worse. And that would only lasted about 4 hours. Because by that time, that sergeant who harassed me went over to the warrant office. He said, what the hell are you doing? So I need Spur. He said, well, why don't you treat him like a regular guy? He said, well, I've been 17 years. And he said, that's not his fault. Use him, use the guy. He says, yeah, he was the only trained guy I got. So we got all 3 of us together in a room, and I said, just treat me like a normal guy. I don't hold grudges. I understand how you feel. And that was it. And I never had another problem. He ended up being a really nice guy. And so anyway, I've had this right straight through. My professor in college, after I got out, same thing. He harassed me, the same thing. And I finally put him up against the wall. I said, we got to do this against each other and see who does it right and who does it wrong. He said, well, forget about that. I'll give you the A. Because he wanted to give me a B. I said, no, you give me an A. I said, I know this stuff better than you. I said, well, let's do it. All right, I'll give you the A. Okay, my outstanding friends. I have discovered that evidence and proof have no substance anymore. Everybody wants to see a pedigree. They want to see you went somewhere to learn something. Well, let me tell you something. I learned from the United States Army. I went in the Army. I volunteered to go in 1968, right when the Tet Offensive started. Stupid, yes, but I did. And they immediately put me into electronics, basically, because I had an extremely high GT score. And I was promoted within 7 months, I was an E5. That's very unusual. That's like a sergeant grade, non-commissioned officer. So I learned a lot from the Army. And I was in the United States Army, Alaska, USARAL, up in Alaska, servicing the Nike Hercules missile sites. Now, from there, I went on, because this was the very beginning of quantum. This was the very beginning of everything with electronics, basically. Before this, the equipment that ran business machines, which you go to the stores, it's beep, 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 boop, 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 everything's scanned and this and that now. Well, back then it was mechanical. I'm not kidding you. You went up and put your stuff on a counter and they went tone, tone. I'm not kidding you. There was no scanning. There was no any of that stuff. And the machine went, there was no light up display, nothing. And this was basically, they would call it National Cash Register, IBM, Victor. Now, I went with Victor. Well, they came to me, actually, because they were going into the electronics. Nobody had any idea about it. These were very old companies. Victor and IBM and NCR, they were basically on the same playing field. They were huge business machine companies. And business machines were mechanical. Now they went to electronic. Now they want to go faster and faster and faster and faster. Yes, I understand this more than anybody breathing oxygen. I'm telling you that right now. My old boss used to say, if it's true, it ain't bragging. And it ain't bragging because it's true. And I will show you it's true. I started when the first business machines came out that were electronic. They sent them to me in Connecticut to test. And they exploded. This is the story. General Instruments made logic chips. Logic was the thinking part of the thing. And then you have driver chips that do the work. And they wanted everything to run at 17 volts. So they put out this 17-volt chip. And in the factory at 17 volts, because of the warmth within the circuitry, there was enough resistance so that the flow didn't exceed its ability to flow. These inside of these little microchips, the filaments are so tiny that if you exceed a certain number of electrons, they explode. Well, they had them in the factories. They tested them out. They were working great. And they sent them up to me in Connecticut. We had a whole batch of them because we used to do Travelers Insurance Company, all the insurance companies up in here, and everybody, and they all had adding machines. That's what they ran everything on these adding machines. So we got any equipment. I said, everybody test these in. So I was the field engineering manager. So I said, everybody get these ready to go, test them out, make sure they're working, and deliver them in the morning, and let's see what happens. Well, they were all working great, and we all made tests. You always put a test tape with the machine. So you say, okay, yeah, we tested it, here's a test tape. Well, as soon as they plugged them in, every single one of them exploded. Every single one. It wasn't just like one or two. And I'm not kidding you, exploded. When I say exploded, a chip has a central core and then a ton of little legs coming out. Years ago, they had, that's how they were. They had literally, I think it was like 100 legs or 64 legs, maybe, I forget now. But they had a whole ton of legs coming out that went through the board and were soldered and all this stuff. Very, very complex and very, very tiny little chip in the center of all this stuff. And the chips exploded. And I'm the field engineering manager. They said, well, what happened? I said, I don't know. So I get them in there, I start looking at them, and sure enough, they all exploded. The only difference that happened was they were cold. And that's all I could come up with, because in New England, it gets really cold in the winter, and they came in the winter, I can't remember when it was, 75 or something, 76, 1975, 76, and in that area. I can't remember now. But it was the first ones to come in from this General Instruments chip, and sure enough, they exploded. So I started looking into the temperature, and I had all the equipment. I'll show you. I got some pictures here from way back in the days before there was really heavy duty electronics. I was there from the beginning, and I know about the weight, because we had weights and measures for the scales, and you could not get a scale calibrated unless it was the same temperature as the weights and the whole room. Everybody had to be the same temperature. It didn't matter what the temperature was, but as long as they were the same temperature, it would weigh correctly. Think about that for a minute. Think about these things I'm telling you. Cold made the chips explode. The temperature had to be exactly correct to get a scale certified. I had weights, and I still have the seal where we used to have to wrap the screws that could calibrate it with these seals and seal the seal with a lead seal. And you had to be certified, and you had to be weights and all that stuff. And that's why I know about this. They had to be the right temperature. Nobody knew why, and they still don't know why. I know why, because temperature is excess electrons. The more excess electrons you have in something, the higher the temperature goes. It's so simple, it's unbelievable. You take something hot and you bring it into a cold room, those extra electrons bleed into the air where the cold will say, come on over here, we'll take you, come on. And they just go out. And they're electrons, and they warm up the air because now they have the excess electrons. Simple as that. It's just like water flowing from one side, from the hot to the cold to the hot. They just go back and forth. They're just little bitty bits that run out or run in. Depends on which you are. So if you bring a scale in that's or you bring in the weights in this particular one time I brought them up there, and they were cold. And I came in and I said, can you certify them? He said, no, you got to leave them 24 hours. So of course, you know, the way I am, I said, "Oh, come on, man! I got to come back here 24 hours. Why can't you do it now? You're sitting down." He had to sit in coffee, reading a book or something. And I said, "No, you have to leave them for 24 hours because they have to stay for 24 hours because they got to be the same temperature as the room." And I said, "Whoa!" And that always got me. So I knew that there was something added or something taken away. It had to be. And if one flowed to the other. It's as simple as that. The electrons have a weight. They have a weight. They weigh 0.00058548 something atomic mass units. And you take 1,839 of those little buggers that slide back and forth as heat, and you put them in a ball together, that's a proton. When they're in the electron phase, they collect electricity, static, lightning, and heat. But once they go into the matter phase where they collect enough of them, they lock in, and that's when you get matter. Okay, this is Sabine Hassenfelder, and she has fallen out with physics and so forth because they're not getting anywhere, because everybody's just trying to puff up their own little things for funding. It's not nothing here as I show you, the stuff I show you can't be denied, and it's been denied for over 10 years. We found the same particles, and I interacted with University of Geneva and Fermilab both, and, well, all of them basically, but very little response. Fermilab, the response was extremely negative and very disrespectful of my research, which was at least equivalent to theirs at Fermilab or better. And again, I'm not bragging, it's just fact. Factual fact. Let me just show you that to get started with. I have validation for everything I'm saying, and I can show you the documents to prove the things I'm talking about this chip being over voltage, and about my involvement in these early days. This is from Victor Business Machines, which became a division of Walter Kidder Corporation. I was the field engineering manager, Eastern Region scoreboard. Attached Eastern Region, My congratulations to all the branches over quarter revenue, The Eastern Region finished with 105% quota. Roger Spur and his Connecticut Yankees finished the last quarter with a combined quota profit objective of an astounding 360%. That's the only reason the region made it. They'll be receiving their plaque and so forth. Gentlemen, 1978 was a great year, Well, that's when I was in charge of the field engineering, because I knew what I was doing. So the profit was very simple to make. The other branches were sending me stuff to fix for them because they couldn't do it. I was supporting this whole thing, basically. Bragging I was just bragging. It's true. And they wanted me to do more. I said, I can't do more than that. I said, I'm working off of things that nobody else could work with. I was fixing things that the previous administrations had never been able to work with. They just piled them up like junk. So I fixed them all up and we sold them. So, that's how you get 360%. You don't just fall off the walls. We didn't hurt anybody. We didn't take advantage of anybody. We didn't do anything wrong. But by this time I had used all of this stuff that was just wasted. And I said, I just made you a whole ton of money. I can't do this every year, because they added more on top of what I did. So I said, that's it, I'm going to start my own business, and I did. And it was very, very successful. Very small. I said, that's it, I don't want to get big. I want to stay small, and it was. But we had the best system on the market. There it was right there, BMSSPOS. Business Machine Sales and Service, Point of Sale. And it was eventually touchscreen. Originally, I'm going to show you the stuff, because these people that are talking out of their minds, that have never touched anything or done anything, or had to go to the weights and measures, or had to go figure out why machines exploded, and why static was a problem, and why grounding was such an issue at a certain point in time. I went through all of that, and I started before that with the Army and the nukes and all of that stuff, and then I went to school for chemistry and electronics and all that stuff. Every bit of it, 100%. Not one thing did I not look into. Quantum was not even really there at that point. They knew there was bonding, and there was orbitals, and there was polar, and there was dipoles, and everything was. Everybody's trying to make a law. There's no laws. Light doesn't go one speed. It can go faster, it can go slower. It slows down as it comes through the universe. It's not just being pulled away. These are problems that once you're menticide, which means you're brainwashed into believing one thing, and that's the law. That's the law. That's a peer-reviewed law. No, there is no laws. If I can prove something, then the law does not apply. If I can prove it, it doesn't work, then the law does not apply. And I have proven it over and over and over and over and over. And the same thing in the mud fossils. All of my research is 100% validated and denied by academia. And she's talking about superconductors. This is another boondoggle. You can't have superconduction. The only way anything superconducts is if there's no resistance. And as soon as you start conducting into it, the resistance starts to grow. they want to make something where they keep sucking off the heat. That takes more energy, or probably at least as much. And then you got to go through all this. She points it all out. She did a nice job. What about this and what about that? And are the crows going to freeze to the wires? Well, anytime anything gives off heat, it requires to put more energy into it to keep it cold. It's like I can't believe they don't understand the concept of heat, and they don't, because they don't understand dipole electron flood theory. Simple as that. Everything is made as a dipole, and an electron is not just a positive, a negative. It's a positive with a negative. The positive is a dark matter. The negative is the glowy, pushy, burny part. The black just moves with it. That's what they used to call a boson, a carrier. I don't know why they went away from that. I'm going to show you all this stuff. So you want to stick with me to learn about how I understand what I understand? I have this all the time. Well, how do you know this stuff? Who the hell are you? Well, who did you learn this from? I learned it from doing it. I didn't have to go learn it from somebody to say, you do this, you do that, and if you do what I told you, I give you an A. No. That's why I had to get out of that realm. That did not work for me, doesn't work for me today, never will work for me. It shouldn't work for you. If it does, you got an issue.